Hello folks, this public keys video guide is designed to supplement the public keys written guide, which provides all project details that include a project summary, key vocabulary and background, list of materials, a procedure, activity extensions for students who need more, activity scaling to differentiate instruction, and a conclusion. Both the video and written project guides assume an audience of non-engineers. But word to the wise for this one gets involved. So there is at least discussion of math. I want to let you know we're going to talk about some math here, but hopefully in as straightforward a manner as possible. Let's get going. This lesson introduces two important internet security concepts. One's called public key encryption, which is done via applied math in a beautiful way, might I add, and one-way functions. These are math operations that are easy to generate, but they're hard to crack or reverse. Easy to do in one direction, they're much more difficult to do in the reverse direction. Student teams will then appreciate that any lock can be broken. Any lock can be broken. And that computer scientists study hard problems to simply lengthen the time that it takes to break that lock. But they can be broken. Now, our approach is a creative variation of tryengineering.com's public keys, one-way functions, and hard problems lesson. Let's get into it. We got some ground to cover here. First up, our vocabulary, which appears there. A lot of terms here. Let's walk through most of them. Okay. First, public key encryption. This is a technique for making some part of a password public because we're all broadcasting across the same network. So everybody's going to see some part of everything, but you want to make it nearly impossible for the secret part of the password to be discovered. That's possible. One-way functions. These are math operations that are easy to generate, but difficult to crack. Easy to solve in one direction, difficult to solve in the other direction. Exponents. Exponents are mathematical notations that indicate the number of times a number is multiplied by itself. Think 2 raised to the exponent 3. Said another way, 2 to the third power. That's 2 times 2 times 2, which is 8. Next up is modulo arithmetic. This is a math operation whose answer is the remainder of good old division. So 12 mod 5 is a quotient of 2 and a remainder of 2. So 12 mod 5 is 2. 13 mod 5 might be a little better example. 13 mod 5 gives us a quotient of 2, a remainder of 3. So 13 mod 5 is 3. The Diffie-Hellman algorithm. Diffie and Hellman are pretty important folks in the world of cryptography and internet security. They developed a recipe that uses exponents and modulo arithmetic to create one-way functions that allow two parties to share information. They're the reason that we are here having this conversation today, so big ups to Diffie and Hellman. Next up is algorithmic complexity. This is a computer science technique for determining how long it will take for an algorithm to produce a solution. It is a cornerstone of security because all locks can be broken. You just want to make it take a long time to do so. And then hard problems. Hard problems are those that take an extremely long time to solve. All right, let's talk one-way functions and public key encryption using Colors. How can two people communicate privately across a public network where you always have spies lurking? But way back in 1976, Diffie and Hellman devised a trick to do this. Now the trick exploits math. Math is a little tricky for some people, for most of us actually. So let's illustrate their trick first with a colorful algorithm. Remember, an algorithm is a recipe. How can the sender and receiver use a secret color to guide and facilitate communication without the spy, that eye in the sky, discovering the secret color? This trick is based on two facts. Fact one, it is easy to mix two colors to create a new color, right? Yellow and blue make green, red and yellow make orange. You can do that. Here's the second fact. It's difficult to separate a mixed color into the colors that created it. These facts present a hard problem, one that's easy to solve in one direction, difficult to solve in the other direction, using colors. Now here's how the trick works, right? And I'm going to put my diagram up over there. We're going to talk through this very slowly, right? First, the sender and the receiver agree on a starting color, and they make this agreement publicly. The starting color will be yellow. So the spy now knows, hey, they're using yellow. Now the sender and receiver then randomly select private colors that they will mix with the public color. The sender is going to choose red. The receiver is going to choose blue. Spy doesn't know that. They're going to mix these random colors with the public color. So when the sender mixes red and yellow, they get orange. When the receiver mixes yellow and blue, they get green. The sender will then keep their private color and send their mixed color to the receiver. So the sender is going to send orange to the receiver. The receiver in turn sends green to the sender, and the spy is going to intercept both of these colors. So the spy has information, but the spy does not know the secret colors for the sender, which is red, and for the receiver, which is green. Now here's the heart of the trick. The sender is now going to add their private color, which is red, to the color they received, which is green. Now, when they add their red to that green, they get brown. The receiver is going to do the same. The receiver has received orange. They will add their blue to orange, and holy moly, they end up with brown as well. So now they can communicate using that shared brown color. This is amazing, right? And I did this in real time at a website called trycolors.com that allows you to mix colors. Didn't know such a resource existed, but it was very helpful in creating this diagram, which hopefully has illustrated this solution using colors. And remember, this is just an illustration. You're not going to create passwords using colors. This is just to illustrate how this trick works. Now let's back it up and do it again and illustrate that whole thing with numbers. Again, I'll go slowly, and we'll keep you as high above the water and the muckety-muck of mathematics as possible. I'll try my best. So to illustrate public key encryption with numbers, we need another kind of one-way function, one that's based on modulo arithmetic, which we talked about in the definitions. Remember, the answer in modulo arithmetic is the remainder of the division operator. So as an example, 7 modulo 2 is congruent to 1 because 7 divided by 2 gives you a quotient of 3, remainder of 1. So the answer we're looking for here is 1. 7 mod 2 is congruent to 1. We don't say 7 mod 2 is equal to 1 simply because that's not how modular arithmetic is defined. Work with me there. So we don't use the equal sign with the 2 bars. We use the congruent sign, 3 bars. Work with me. It'll come out in the wash. Another example, 46 modulo 12 is congruent to 10 because 46 divided by 12 is 3, quotient 3, remainder 10. Now let's choose 2 numbers to get started with this part. We're going to use the number 17 as our modulus. Why? Well, because 17 is a prime number, and prime numbers, especially large prime numbers, are very hard for the spies and the bad guys to crack or to guess. And we want to use the number 3 as our generator. Why? Well, it just so happens that when 3 is raised to an exponent, the operation 3 raised to the x power modulo 17, that answer is equally likely to be an integer, a whole number between 0 and 17. So we're choosing a problem that will give us an answer between 0 and 17 because we got to have some structure and management and how this whole thing is set up to make it all work. But that's why we want to use 3 and 17. Using 3 will make the operation easy to solve in one direction. You know the answers between 0 and 17, but it'll be difficult to solve in the other direction because the bad guys are out there. We don't want them to be able to solve it. All right, now let's use this table to organize what's going on, and I'm going to talk through it again very slowly, and then we're going to move forward from there. All right, so we know that we've chosen 17 as our modulus and 3 as our generator, and we share that publicly so the spy knows that as well. We're going to both choose secret numbers though. The sender is going to choose a private random number of 15. Sender is going to use a private random number of 13. Spy does not know this. Sender is going to calculate 3 raised to the power of their private random number, which is 15. They're going to do 3 to the 15th power modulo 17, which is 6. They're going to send that 6 to the receiver. The receiver is going to take their private random number and they'll do 3 raised to the 13th power modulo 17, which is 12. They'll send that 12 to the sender. The spy is going to pick up both of those numbers. They've got the 6, they've got the 12. Here's the trick. The sender is going to take 12, the number they receive from the receiver, and they're going to raise 12 to their private number 15. They're going to do 12 to the 15th power modulo 17. They get 10. So that will be the number that ensures their encryption, their password, if you will. Likewise, the receiver is going to take the number that they get from the sender, 6, and they're going to raise it to their private number, the 13th power. They're going to do 6 to the 13th power modulo 17. And lo and behold, they also get 10. Now, is this a coincidence? No, no. This is a beautiful application of math, one that's so beautiful, it's worth looking under the hood and understanding how that comes to pass. I'm not going to bother you with that in the video, but I will say in the project guide, I do what I call a slow motion derivation so that those who are interested can see how beautiful math is applied and even exploited in this process to allow what I just described to be true in every sense of the word every time you do it. So I encourage you, take a look at that derivation, or have a friend of yours who's really into math take a look at it. Keep me honest, and let's make sure that there's a deeper understanding for those who want it. But if you're okay with the result that I presented, we can move forward. Now the SPY will probably not be able to crack the encryption in a reasonable amount of time, but it can be done. And I've told you, we set the problem up so that it gives us answers between 0 and 17. SPIs understand that, so they understand how to structure their approach to cracking. It's just a matter of whether they can get it done in time for it to matter. Materials for this project: handy dandy engineering notebook with pens or pencils, and then small tokens like coins, stones, bag of stones, wrap candy, something you can use to demonstrate modulo arithmetic. That would be helpful, because that remainder concept is hard for people to wrap their minds around. It's easier if they can see it. Regular old scientific calculators, one for every 3 students, would help, because you can do modulo arithmetic on any scientific calculator. It doesn't require anything special. I won't dive under the hood on that one, but I place an example in the project guide to show you, here's how you do modulo arithmetic using a regular calculator that only has addition, subtraction, multiplication, division. It is very possible, very straightforward, but I put that in the project guide. And then the last material you'll need is a timer, like a wall clock, or the egg timer that I provide in several of our projects that you can download from our website and use for free. You may not use the timer, but just have it on hand. All right, our procedure. There's a video on public key encryption that explains all of this and animates it in beautiful fashion, and it probably is a good idea to allow the students to watch it. So I'd say use it, and then consider slowly reteaching that color mixing example using the approach outlined here. If you're brave, you may even want to go to trycolors.com and try to recreate the colors yourself. That's not necessary, but if you want to, that wouldn't be a bad idea. Watch the video in its entirety, but perhaps break it up. Watch the first half, watch the second half, and then move towards demonstrating the concept of exponents to your students using your set of tokens, your coins or your rocks. Use a base of 2, because doubling is kind of easy to visualize. Show them that 2 raised to the first power is 1, and that 2 raised to the second power, 2 times 2, that's 4, and 2 raised to the third power is 2 times 2 times 2, that's 8. Show them for 3. 3 raised to the first power is 3, 3 raised to the second power is 3 times 3, etc., etc. Next, you want to demonstrate the concept of modulo arithmetic using a base of 3. You start with 9 tokens, divide those 9 tokens into 3 groups, which result in a remainder of 0. Explain to them that 9 mod 3 is 0. Now divide 10 things into 3 groups, you'll have a remainder of 1. 10 mod 3 is 1, so on and so forth. Demonstrate it until they get it. Then assign students to teams of 3 and to do some practice with exponents. Now you can make these problems up and even check them on the calculator before you write them, wherever you write them, on the board, or if you say them out loud. Do things like 4 raised to the third power, 2 raised to the fifth power, 10 raised to the fourth power, 8 raised to the third power. Do these until the students become comfortable with the exponents, because they're going to need this. Do the same type of practice with modulo arithmetic. 11 modulo 4. Well, that's 3 because 11 divided by 4 is a quotient of 2 with a remainder of 3. Do those until you're comfortable with them. I include a link to a modulo arithmetic calculator that you can use to check your answers. And then practice exponents and modulo arithmetic together, because the Diffie-Hellman encryption method relies on the fact that raising a result to another exponent is equal to multiplying the two exponents. That's part of that derivation that I put in the project guide that I didn't go through here in the video, but I'm going to throw up the equation right here so you can see that that is a very important part of the trick, that this operation is true. Convince your group that it's true. If you have to, just multiply 2 by itself 12 times, but show them that this is true. It'll help. All right, and then what we'll do to finish this off is we're going to create a one-way function with secrets similar to the previous example, where you're going to use the Diffie-Hellman trick and the math using 17 as the prime modulus and 3 as the generator, knowing that those numbers are public. And then with each team, you'll assign 3 roles. You'll have a sender, you'll have a receiver, you'll have a spy. And I provide a worksheet that you can provide to students, that you can also use yourself to help organize the work so that it goes according to the example that I showed earlier, where the sender and receiver both choose random private numbers that the spy cannot intercept. They both calculate 3 raised to the power of their private number mod 17, and they get results that they then send to each other that are also intercepted. And then they take the results that they get from each other and use them along with their private number to create a shared secret result that becomes the password. That's what you'll actually do. Now, the spy has a special role in this process. The spy's job is to crack the code. And it can be done. Remember that the design of the problem is such that it gives us answers between 0 and 17. Now, once the spy understands that, the spy says, I've got to raise 3 to an exponent. And at some point, raising 3 to an exponent doesn't even give you a number. So all I've got to do is calculate exhaustively all the possible exponents starting at 1 and going as far as 27 to see where it blows up and gives me a number so big it's not even a number. It's not something Microsoft Excel will even calculate for you. That exponent is 27. 3 raised to the 27th power gives you a number. 3 raised to the 28th power blows up. So you've only got to calculate 3 to the first power through 3 to the 27th power. That gives you a chance to crack that code. Matter of fact, I crack the code, and I provide a spreadsheet to the instructor of how I crack that code. You can simply open the spreadsheet and plug in the sender and receiver's calculated values, and it will show you the secret numbers that can be discovered by the spy. If the spy is swift in mathematics, you should assume that you will have a student that can crack that code, so you need to be ready with your code crack generator yourself so that you will be able to understand and verify whether or not this student has cracked the code. If you don't want that to happen, you can set a time limit on the spy's work, but I kind of would encourage you to see if somebody can be successful in cracking it, and then it tells everybody what I've said throughout this video. Any lock can be broken. You just want to make it take a long time to do so. Speaking of long time, let's get this video wrapped up. Extensions for students who need more. That spreadsheet resource that I mentioned, it's a great extension. It'll allow you to stay in front of your students and be able to see how to crack this password, how to do the spy's job. You can also allow your senders and receivers to use Microsoft Excel to do their calculations. It's a one-stop shop. Microsoft Excel has a modulo arithmetic function, and of course it does exponentiation. And you can consider spending more time reviewing exponents in modulo arithmetic. How do we scale this? You can have your student senders and receivers work in pairs and not have a SPY. Everybody focus on calculating and nobody worry about spying. Or you can spend more time reviewing exponents and modulo arithmetic. And I'm sure this is the most mathematical of all the projects that we have done. So take your time with it. I've taken my time to explain it and provide detailed mathematical explanations for those who want them in that written project guide. Have fun with it. Take your time with it. This one is kind of involved, but that's what makes the learning fun. Take care.